Yeah, guten Abend, good evening, everyone. Welcome to brand new edition of Astronomy on Tap Bonn, the first one in this year. And unfortunately, we are still virtual, but that doesn't mean that we cannot have a little bit of fun. Today on the menu, we have an amazing talk by Dr. Eleni Vardoulaki that I guess a couple of you already know from AOT. And then after that, there will be a premiere of our science or fiction game, and a little bit more on that in a minute. First, let me just reiterate, you can contact us at any time with any astronomical or non-astronomical question that you have. Here on YouTube, we're also on Facebook, Twitter, Instagram. You can write us an email if you want to. And most importantly, we are always looking forward to interacting with you in the chat, just on the side of your screen. So just write into it if you have a question or anything else. And interacting in the chat is especially important today because we are going to play science or fiction. Now, how does that work? Well, you know, usually as astronomers or as scientists, we are used to telling the truth, but sometimes we don't. And today, some of us will present some interesting facts that are either true or false. And you can watch us here on the stream and decide for yourself which one of these persons is telling the truth and which one is lying. Then write it into the chat, tell us who you think has told the truth. And then from the people that participated in our awesome game, one person will be picked and they will win an awesome ESO calendar. And these are just some of the pictures that are in the calendar. It's really a great calendar. So I'm really looking forward to this, and I'm really looking forward to all the interesting lies and truths that will be told. And but before all that, we will first have a really nice talk by a guest that we have been missing a lot here in Bonn. Dr. Eleni Vardoulaki, and to introduce her and to moderate us, I introduce Felix Pötzel, who will be the moderator for this evening. So, Felix, take it away.
The great introduction. As you said, we will have a fantastic talk today by Eleni, which if you have followed Astronomy on Tap for some time, you will know her already. She's the founder of AOT Bonn. So in that sense, we are all here because of her. So thank you. And yeah, I'm happy to introduce her to you today. And she will talk about how our universe began and how we can observe that. Like how do we know exactly why that is the case? So yeah, say hello, Eleni.
Hello, good evening. Thank you very much for the invitation. It's great to see you again, guys. I have missed you a lot. And I wish we could do this in a pub. So let's keep our fingers crossed. Right.
So although we are not in a
screen.
although we are not in a pub, so feel free to grab any beverage of your choice.
I do have I do have this fantastic pint glass AOT Bonn that you guys gave to me before.
Mine is not as cool, but
mine was custom made. It was custom made.
Yes, it looks awesome.
Okay, so today I want to tell you a little story about how the universe, how everything was created, you know, in the universe. So it's like a story told to kids or big kids that like to hear stories about the universe. So feel free to interrupt me at any point, you know, like kids do to their grandparents when they tell them stories, you know?
All right, I will.
Yeah. So let's start. A long time ago, something unexpected happened that changed our understanding of how the universe was created. And this story I'm going to tell you today involves two radio astronomers, Arno Penzias and Robert Wilson. Let me move, please. Okay. So these radio astronomers were working for Bell Laboratories, and in the 1960s, Bell Laboratories built a radio antenna, this big 15-meter long antenna. It had a very peculiar shape, like a horn. You can see it's very different from what we are used to. So the purpose of this instrument was to amplify and transmit signals to long distances. So the purpose was telecommunications. So it was making the signal more intense, so it would reach further away. But in the 1960s, also there was a launch of telecommunication satellites. So this antenna became obsolete. And then Penzias and Wilson took the chance and used it for science, right? So they wanted to investigate the radiation that was coming from the space between galaxies. And in 1964, they discovered a radio signal that was very different from anything they have observed before, anyone has observed before. The signal was so bizarre that initially they thought it was noise, okay? Or maybe some interference from something man-made, or maybe from the pigeons that were living inside the antenna, because as you can see, it's quite big.
There are living pigeons inside the antenna.
Yes, they had pets, the radio pigeons. And they cleaned the antenna and, they tried again. But the signal was there, okay? They were convinced it was not coming from the Earth, and probably it was not noise, because it was there in all their observations across 4 seasons, okay? And it was coming from everywhere around us, not from a specific direction. So they didn't know how to interpret this signal, okay? It was really, really puzzling them. But let's take it 60 kilometers away. So Holmdel antenna was in New Jersey. Now we go to Princeton, and Robert Deakin, yes, Jim Peebles and David Wilkinson were working on theories about how the universe was created, okay? They were trying to understand how we can, about this relic radiation, that was left after the big explosion that created our universe. And they found out about this discovery, and they matched together observations and theory, and realized that this signal that Penzias and Wilson observed was the relic radiation from the big explosion that created our universe, the signature of the Big Bang, if you will.
So they expected some signal, and they just coincidentally found it with this old telecommunication antenna.
Yes. So it was a serendipitous discovery. This is what we call in astrophysics a serendipitous discovery. So there was a theoretical background that, something should be discovered, but no one had discovered it yet until 1964. And this signal that was coming from outside the Earth, right? From the very distant universe, from a time where the universe was much younger than it is today. It's what we call the cosmic microwave background radiation, or CMB. And this is the leftover radiation from the first explosion that created the universe. And for this discovery, they got awarded the Nobel Prize in 1978. So it was very, very big discovery.
Very well deserved.
Yes, and it's amazing because they used an instrument that they didn't have the purpose to be used for astronomy, right? The purpose was telecommunications, and they converted it to use it for research, and they discovered something amazing, something that we believe today to be, common knowledge. So the cosmic microwave background radiation is the evidence that we need that the universe expanded from a hotter, denser state. So it was very hot and dense in the beginning, via a violent explosion. And this explosion left a fingerprint of electromagnetic radiation that traveled millions and billions of years to reach us here on Earth today. Okay, but let's take it a step back. Let's go back to the beginning and discuss how it all began. And I will give you an analogy. I like describing astrophysics through analogies. You know me. So for me, for me, the beginning of the universe is like an idea. An idea that was not there before, but suddenly it appeared in my head. A unique idea. And the clock for this idea starts running the moment the idea appears in my head. And it grows with time. It grows and grows and grows. And just before it's ready to leave my head, right? You don't know my idea. I have not told you my idea. You, the audience, don't know my idea.
I have no idea what is your idea.
Yeah. You have no idea. And so you have no idea what I'm thinking because I haven't told you, right? Everything is inside my head still. I haven't verbalized it. I have not acted on it. So you will only be able to know my idea when I act on it. Unless you can read my mind, Felix, I don't know. You have any instruments that you can read my mind, but this is another story, and you can ask for this later in the questions. It's about gravitational waves. So the point, this is very important. The point that my idea becomes known to you, the audience, and it becomes action is in universe terms when the universe became visible to us. Okay, so there is a moment in time that the universe becomes visible to us, and this is the surface of the cosmic microwave background. This is when the universe became visible to us, like my idea, right? This is the analogy, but let's go back a bit to universe terms. And let's put the story together. So Penzias and Wilson discovered this radiation from the surface of the cosmic microwave background from when the universe became visible to us. Okay, and in order for us to understand what happened, we need to study these first moments in time, so when the universe was very small and young. Current cosmological models tell us that the universe was born from nothing. There was no meaning of time, no meaning of space, nothing existed. Okay, this is a very difficult concept to understand. You know, how can something be created from nothing, right? The real answer is that we don't know. We don't know if there was something before. There are theories of multiple universes and other theories of what could have been before the beginning of our universe, but we don't have the observational evidence. We don't have the observations to back up these theories yet.
It's right? Just ideas.
We have ideas, and it's good because, you know, once we get the observations, then we can verify our theory. So by studying these first moments in time, we can understand how the universe was created. So what happened? Suddenly, space and time are born, okay, from a point of infinite density. This is what we call the singularity, and it's born in a big explosion. And the first moments in time, the universe grows very rapidly, big, you know, by a big factor. This is a huge number. Don't get intimidated. This has 26 zeros. It's a very big number. Imagine if this was money. Huh? Yes, it's a very, very big number. And this is how big the universe becomes. But this happens in a very small amount of time. Also, don't get scared by this very, very small amount of time. This is 32 decimal points. Okay, so we cannot even describe it. We don't have a feeling for how fast this happened. But if you are a parent, you do have a feeling, you know, because this is how long you have for yourself when you're raising a family. So no time at all.
That might be true at these times, yeah.
Yeah. No time at all. 32 decimal points. And then the universe starts growing. after inflation. That was the inflation, the time of inflation, and it starts growing, and everything starts being created. You know, the atoms. Atoms are composed of nuclei, so this is the time of nucleosynthesis. This is what it's called, and the universe is very hot. It's a few million degrees Kelvin, and it's still invisible. It's behind this curtain of the cosmic microwave background surface, okay? So we cannot see it. It's like my idea still inside my head. You cannot see it yet. And then something happens, and matter becomes visible, and we have a combination. And this is the time that, the time in cosmic time, let's say, that Penzias and Wilson observed with a Holmdel antenna, and it is 308,000 years after the Big Bang. So it's a long time that the universe was not visible to us. Things were happening, atoms were being created, and then all of a sudden it becomes visible to us.
So this is the oldest radiation from the universe that we can actually observe, right?
This is the oldest thing that we can observe with our current telescopes, okay? With electromagnetic radiation that we can observe with our telescopes. And they observed this, as we said, in 1964. And this is the relic radiation from the explosion, the Big Bang, okay? This is what gave the evidence that there was a Big Bang. So it's a huge discovery. And it was verified later by satellites, telescopes that observed again the cosmic microwave background, like COBE, WMAP, and Planck, but in finer detail. So we have more detail of this surface, and we will talk about it a bit later. So after that, the universe starts cooling down, you know, it's not so hot anymore. Down to 3,000 degrees Celsius, 3,000 Kelvin, 2,800 degrees Celsius. And to give a bit of an analogy, this is quite hot for us. I mean, in everyday life, for example, I'm hungry a bit now. So you cook a chicken in the oven for an hour and a half at 180 degrees Celsius. So the universe is still hotter than your chicken at the moment.
Like almost like the surface of the sun still, right? Which is
yes. But still, we don't have a feeling for that, you know? But, you know, yes. We have a feeling for the hot chicken in the oven.
Now I'm getting hungry as well.
And now I'm hungry more. So the time that the universe cools down, matter starts interacting, and we have the creation of hydrogen. And this is when the universe becomes visible, as I said. So in my analogy is when my idea becomes visible to you, when you get to know what I'm thinking.
Basically. So when you speak up about your ideas.
Yeah, or I act on it, you know, I do something.
So the universe started speaking at some point when you
yes, I'm like, I'm here.
Phrase it like way.
Hello. So, and what we have is what we call the fingerprint of the Big Bang, of the initial explosion. And we compare it to models, many models. We do some forensic astrophysics. I really like this. If you like CSI, I like this term, forensic astrophysics. And we try to understand how the universe was created, you know, because we have our observations, but that's not enough. We still need to base a lot of our understanding into models. And what we observe is not homogeneous. It's not smooth, okay? There are fluctuations, anomalies in this surface of the cosmic microwave background. And it's not smooth like the skin of a baby. You know, the skin of a baby is very smooth, soft. It's more like the skin of a teenager going puberty. It has these bumps. And this is one of the data from the later satellites. This is the latest Planck satellite. So it's very good definition, let's say, in everyday word. And these fluctuations are very important, right? Because these are the seeds from where the first galaxies are born. So from these anomalies, eventually galaxies will be born. They will evolve in cosmic structures that we observe today. So everything we observe around us, the stars, the planets, the galaxies, the galaxy clusters, start from there, from these seeds.
Wow.
And this is quite amazing if you put it all together, right? That's why it's such an important discovery. Let me have a sip and I will tell you more.
I think this is very exciting.
Yeah,
to see these
I think
galaxies that early in their formation, just before they're born.
Yes, I mean, everything has to start from somewhere. And with these observations, we were able to pinpoint where this started from, how it started. So how much do we know, right? How much do we know about the universe? We are humble people, Felix. We know, as astrophysicists, we say we know some. We know a few things about the universe, but we don't know everything yet. But we
so
discover,
much that we don't know.
Yeah, we discover more and more every day. For example, let's say a few things that we know. We know that the universe is almost 14 billion years old. To be exact, 13.8 billion years, and that's 13.8 with 8 zeros after it. It's a very huge number. And I will give you another analogy from family life, because I'm going through it. This is how long it takes for your child to get ready in the morning so that you can take them to school. It's a true story. Yes, right. Okay, I love this one. This is why I put it here. To get a feeling of how old is the universe. Okay, we know it's almost 14 billion years old, but if we compare it to our life, so imagine that the universe lasted 1 year and it started at January 1st. Then humanity is alive only the last 0.32 seconds of the night of December 31st. Okay, the end of the year, the very, very end of the year. So we're
you have to zoom in to even see that in the calendar.
It's down here. I don't know if I have a cursor. No. Okay, so it's down here, nothing. And this is how long it takes for our eyes to blink. This is how long this is. It's nothing. So it's an amazing analogy to understand how that we're not here for so long.
Now I feel pretty insignificant.
Yeah. Or how long it took for us to get here. It's an evolutionary discussion,
True.
What else do we know? We know from observations of the cosmic microwave background and from our theories, so from comparison of the two, we know the cosmic recipe, the ingredients of our universe. So everything that surrounds us, matter, we call it baryonic matter. So everything we see, okay, like my glass, my beer, me, the table, the room, this is visible matter, baryonic matter, the galaxies we see, the stars. But this is a very small percent. It's almost not even 5% of the cosmic ingredients of the universe. So where is the rest of it? And in what form? This is what we want to answer as astrophysicists. Is it hiding from us? So as a matter of fact, it is. This is why we call it dark matter and dark energy. And through, as I said, the observations, comparison of observations with simulations, we try to understand what this is. So, dark matter. I get this question all the time, like, what is dark matter? Okay, everyone.
Exactly. What is dark matter?
Yeah, what is dark matter? Damn it. So, dark matter, I will tell you how to imagine it, because we cannot observe it. We don't have direct observations of dark matter, okay, because it does not interact with visible matter. But imagine it as the invisible skeleton upon which everything will be built upon. All the galaxies, everything, the cosmic structure of the universe, like our skeleton, and our body is built upon that.
That's what we see in the video, right?
Yes.
Skeleton.
So these are simulations. This is the illustrative simulation, and it's not observations, because we have not directly observed dark matter, but we have observed it through effects to the matter, through gravity, not because it does not interact with visible matter.
Yeah.
So this is 27% of the ingredients of the universe. So we are still missing a very, very big percentage of the ingredients of the universe, right? And we call this dark energy, and we have no freaking clue what it is. we really don't know what it is.
How do we know it exists?
From our theories. It has to be there. It has to be there. From our theories and the confirmation from the data that we're getting from the cosmic microwave background observations. Everything matches. So it should be there. We just haven't detected it yet. And we cannot see it. But we know a few things about it. Okay. So we know that it goes through, dark energy goes through the whole universe. It was there from the beginning. And this is very important. It is responsible for the accelerated expansion of the universe. I will explain. So this is 68%, okay, of the ingredients of the universe. We know that the universe is expanding. So, you know, like having a balloon, blowing a balloon, and it becomes bigger and bigger. But this is happening in an accelerated way. I will give an analogy. In the same way, you have a car driver and they are speeding, and the car is going faster and faster. Okay, so dark energy is the driver of the universe and is pushing the gas pedal for the universe to go faster. This is what we know about dark energy at the moment.
That's a good analogy.
Thank you. I like it very much.
So yeah.
Yes, it's very hard to understand this, you know. So we can only give simple analogies to everyday life, even for astronomers, because we have not observed it. It's only through our equations and our theories that it comes out. But we're hoping that in the next, I don't know, decade, it's one of the things to be discovered, maybe through Rosetta, hopefully.
That would be cool.
So let's talk about the future, right? Since we talked a bit about the past, let's talk a bit about the future. What will happen in the future? Can we predict the future given our observations? So we have the observations from the cosmic microwave background, we have our theories, and we want to know if our universe is going to continue expanding and accelerating, you know? So from this comparison between theory and observations, so the other possibility is that the universe will crash, so it will not keep expanding, it will keep start shrinking, and it will collapse into a singularity in the same way it started. So this is one of the theories.
Oh no, I don't want to be crunched by the universe.
The big crunch. So there are theories like that that say universes, you know, expand and then they collapse and expand and collapse and expand and collapse. It's one of the theories. But our current data tell us that the universe is flat, as you see here. So the middle one. So this is the geometry of the universe. It's flat. It started from a Big Bang through a period of inflation, and it's accelerating. It's expanding in an accelerated way. So this is what we know at the moment, and it will keep accelerating, expanding in this rhythm.
Good to know.
Yes, I mean, it's good to know a bit what's going to happen to us.
Yes, exactly.
Right. So we also know what the universe, so that the universe is made out of galaxies, right? Hundreds and billions of galaxies. And every galaxy is made up of stars, hundreds and billions of stars, and dust and gas and dark matter. So the question is, how from the cosmic microwave background we came to the stars, galaxies, galaxy clusters. We discussed about the seeds, you know, so it started from there. So there's a whole field of astrophysics, galaxy evolution, that tries to understand how galaxies were created and evolved to the galaxies we see today, like our own galaxy, the Milky Way. Observational results from WMAP tell us that the first stars were created 200 million years after the Big Bang. So because of gravity, matter gets attracted to each other, and it's concentrated in one spot. And then the first stars are created. Okay, so matter gets accumulated, as we say. It comes together. And by adding more mass to the recipe, they grow larger and larger. And then this is the time where nuclear reactions start happening inside these bodies. And they start burning hydrogen. So this is the first reaction that happens, hydrogen into helium. And this lasts another 200 million years before they start becoming bright. So before then, they're not bright. But what about galaxies? The truth is we have not observed the first galaxies, how they were created. But our theories tell us that theories, models, simulations, like the illustrious simulation here, where you see the dark matter, the cosmic web, tell us that the first galaxies were created when dark matter collides with each other, okay? And it creates knots of mass on the cosmic web. So imagine having a rope. I don't have a rope. Oh, I have a scrunchie. And you're making a knot, okay? Let's see. So you make a knot. So this is where the galaxies are going to be created on top of these knots, like you can also see in the video.
It certainly looks like knots, yeah.
Yeah, I mean, it's an amazing, I love this simulation. I absolutely adore it. And then the first galaxies, they will start colliding with it. They get attracted because of gravity to other galaxies, and they start colliding with each other, okay? And they become one. And this bigger galaxy attracts other smaller galaxies. They interact with each other, they dance, and they become bigger and bigger and bigger. And they end up in the big galaxies we see today in the local universe, like Andromeda or our galaxy, okay? And then this brings us to our own galaxy, the Milky Way. So this is a view. These are the stars inside our galaxy from the Gaia mission, the satellite that observed the neighborhood, our stellar neighborhood, basically. And
so I can see some of the stars moving.
Yeah, the movement of the stars in this stellar neighborhood, not the whole Milky Way. And our Milky Way, like other galaxies, is composed of stars, like we see here, billions of stars, and of course of dust and gas, and as we said, dark matter. And then we come to the Earth. And this is the place where we observe the cosmic microwave background radiation. So now the universe has cooled down to 2.7 degrees Kelvin. This is minus 270 Celsius, degrees Celsius. So we know water freezes at 0 degrees. So this is much cooler than ice, let's say.
And much cooler than at the beginning.
Yes. Oh, definitely much cooler than at the beginning. So we're talking about millions of Kelvin degrees at nucleosynthesis. And now we're talking at 2.7 Kelvin or minus 2.70 Celsius. So it's very cold. And this is the discovery, actually, the serendipitous discovery that helped us put together the pieces of the puzzle called Big Bang Theory. And I will finish. I think it's a very important message that we're not, as scientists, we're not passive recipients of the unexpected, but we actively create the conditions for discovering the unexpected. So give us funding and we can discover more. So thank you very much.
Well, thank you. I like the conclusion to give scientists more money, of course.
Absolutely. Yes. If this hasn't convinced you, I can talk more.
Yes. And I really like this quote. It's like, it's really inspiring.
Yes, even, so think about it, even Penzias and Wilson were looking for this. We're looking for something between galaxies, you know? They were not just pointing the antenna to the unknown. They had an idea of, you know, maybe we will discover something, but they could not really pinpoint what it was. Because also astrophysics at the time was different. Now we have big collaborations. Everyone talks to each other. The virtual world helps a lot. So we know what's happening in every field. We know, we collaborate, theorists collaborate with observationalists and people doing simulations. So all this together, this big collaboration helps progress come faster, okay, and discoveries come faster. And it's quite different from how astronomy was done in the past, where you were a radio astronomer and you were only doing radio astronomy. But now you're a radio astronomer and you will also have to do optical, infrared, X-rays, and to understand and do a multi-wavelength, as we say, study.
I like that a lot, and I do that as well. So it's it's really true.
I will stop sharing now.
All right. Do we happen to have a question from the chat? If so, we might have just a little time to answer it. So
I can. You can ask me about how you can read my mind. I planned it.
Well,
question.
well, I don't know if I can do it.
No. So the idea behind this, why I mentioned that, it's not random, of course. So as I said, we don't know what is behind this veil of cosmic microwave background radiation. Okay, we cannot see behind it. With our telescopes that detect electromagnetic radiation, so light, okay, they detect light in different wavelengths. But we will be able in the future to detect gravitational waves coming from this explosion, from when the universe started expanding. So future detectors of gravitational waves like LISA, and I don't know what comes after LISA. I'm not
like the space interferometer for gravitational waves, right? Yeah.
We have LIGO and Virgo that detected the first gravitational waves from the collision of black holes, stellar black holes. So they were from the stars evolving into black holes, and they collided to each other and they produced gravitational waves that we detected here on Earth. But the space gravitational wave detectors will be able to detect larger signals from further away. Okay, so one of the ideas is to use that to detect gravitational waves from the beginning of the universe. So we can see behind this veil. And this is how you can read my mind.
Yes, this is very exciting.
Yeah.
It is an edge of reading. The mind of the universe is really appealing. Okay, just I think in the interest of time, we should move on. Maybe we have a little time to answer questions later. So maybe keep them going in the chat. So maybe we have some time at the end to answer them. Okay, let's move on to our second part. And thank you, Eleni, for this great talk.
Thank you. I really enjoyed it.
Okay, our the second part it's sort of like our quiz we do, but in a very much different format. So let me tell you again how it works, just shortly. So we will have 6 questions, and there are 2 possible answers that you can choose from. And our professional team of astronomers that we have here will share the responsibility of giving you 1 answer each. There will be 2 answers for each question presented by different people. And you get to decide who tells the truth. So just pick one of them. Just so you can write their name in the chat. And then you can, in the end, just participating in our quiz is enough. So you don't have to be correct all the time in the answers that you give. We will choose a winner for our awesome ESO calendar. So yeah, we would really like you to participate in this. So let us start. Just everyone get on stage, on the virtual stage.
Hello.
So,
Hello.
So we have Sandra, Sven, and Maud here. who will present the answers. And let us start with the first question that we have prepared. So the first question is, what is the color of the hottest stars? So we will start with Sven presenting his answer to that question.
So yeah, the hottest stars in the universe are red, and I'm going to explain you why. So stars normally, for most of their lifetime, produce energy by fusing hydrogen into helium. And once they are unable to do that because they've exhausted their hydrogen supply, the core of the stars contracts more and more and more until it gets hot enough to fuse helium into heavier elements. And this is called the red giant stage of stars. And these red giants are the most luminous stars that you can get. So for example, Betelgeuse is 500 to 600 light years away from us. We don't know the exact number, but it's still one of the 10 brightest stars in the entire night sky. Whereas the closest star, Proxima Centauri, is only 4 light years away and is not even visible to the naked eye. So these red giants with their ultra hot cores are the hottest stars in the universe and the brightest. And that was exactly 1 minute. I'm very proud.
Okay. So thank you for that explanation. But we have a different answer to that question. So Maud, please go ahead. You also have 1 minute to present your point.
Thank you. So no, the color of the hottest star are blue. And the reason why is that the color of a star depends only of its temperature, and the hotter it is, the more it will emit to high energy wavelengths, such as blue and ultraviolet, for example. And the colder it is, the more it will emit to low energy wavelengths, such as red and infrared. And an example of that in everyday life is if you have ever seen a blacksmith beating the metal with his hammer. When it gets hot of the oven, the metal is white, yellowish, very, very hot. And when it gets colder, it gets red, almost, very dark red. So that's why the stars that are the hottest are the blue one.
Okay, thank you. You were also right in time. So now I will give you in the chat just a bit of time to think about it and give your answer. Who is correct in this case? So what is the color of the hottest stars? So I think I'm getting some feedback that I didn't share my screen properly just now when I explained the game, but I still hope you got it. Okay, so I think it's enough time. So now we can come to the conclusion. So the correct answer is that the hottest stars are blue. So maybe Sven, explain to us why it was not correct.
Yeah, so I did not technically lie to you. I was just misleading you. Well, it is true that the core of the star gets insanely hot in the red giant stage. The outer shell of the star is actually quite cold. And yeah, the color, of course, comes from the outer shell, and they're only so luminous because they are so big. It has nothing to do with their temperature. So yeah, I didn't lie in my defense. I just presented facts in a misleading way. Sorry.
I think you presented them in a very nice way. So I mean, since I studied astronomy, I knew the answer, but if I didn't do that, I could be convinced. Okay, so we can move on to the second question. You might have gotten a hint from the talk for this question. So if you paid attention, you might have an advantage. So the question is, what are the oldest objects we observe? So are these either star clusters or planetary systems? And we go first with Sandra. So please make your point. You have 1 minute.
Thanks, Felix. Yeah, what are the oldest objects in the universe we observe? It's star clusters. Look at the theory. After the Big Bang, the universe was filled with only the lightest elements, hydrogen and helium. They make big clouds, which collapse. So the first things that come out of that are stars, and usually a bunch of stars emerge from one big cloud. That is what we call a star cluster. So this is the theory. It's just the only natural way how you can start from having nothing to have something made of elements. Now you may say, yeah, maybe, but there can be big planets around there also made of light elements. Yes, but stars actually produce light on their own. And everything that produces light on their own is generally a bit easier to observe.
Okay, thank you, Sandra. Also just in time. So, but maybe it's not star clusters, but planetary systems. So, Maud, please make your point.
Yeah, the oldest objects in the universe are planetary systems. And the reason why is that when you have a gas cloud that collapses under gravity, it's going to form a rotating disk. And this rotating disk is going to push away the heavy elements, the rock-like elements. And because they are outside of the rotating disk, they are going to rotate faster, and they will form planets that are small in a very short amount of time. And the star in the middle, which is much, much bigger and rotates way less fast, will take much more time to actually be formed. That's why the first and oldest objects in the universe are planets and planetary systems.
Okay, thank you, Maud. But who is correct here? And who told you a lie? So you can decide now in the chat who made the better arguments and who convinced you. Okay. I guess they both will say that they're correct. So, but what is the correct answer? So, it is star clusters. Correct. So, I see that that's a very nice crown that you have there, Tanda. It's the crown of the one who's right. So, but Maud, why were you wrong?
Yeah, I was wrong because, as Sandra said, the universe started with very little, with hydrogen and helium only. And with that, you can produce only very hot and condensed gas, which is basically what a star is. And then the heavier element that forms the planet we know today, they have been created by the fusion inside the core of the stars. So all the very heavy objects that compose our body were actually produced in the heart of a star, which is really, really cool. Yeah.
Yeah, Eleni in her talk just told us that where the first stars and galaxies emerged, right? And all the elements come from there somehow, from stars. I think this is very, very inspiring also. Okay, so let's get to the next question. Might also have gotten a hint during the first talk. So we want to know, what is the fate of our universe? And our two answers there are either a big crunch or the big freeze. And first, please, Sandra, go ahead and
Yes.
make your point. 1 minute to go.
Thank you, Felix. So what is the fate of the universe? It's obviously the big crunch. Think about it. The universe started after the Big Bang and expanded, just like Eleni explained to you. You can visualize that if you throw a ball upwards, it goes up, up, up. What happens? Gravity will take over and pull the ball back to the ground. So eventually you'll stop going up, you fall back down. That's exactly the same thing that happened to the universe. You have universe starting to expand fast first, and then slower. Eventually, will stop. It will fall back together. This is what we call the big crunch. And if you have it in your head, there's no way that gravity could act as a pushing device. It's always something that pulls. And there's nothing known in the universe which actually on these large scales can push things away from each other. So the only fate the universe can have is a big crunch.
That was 59 seconds. So very, very on the point in the time. Okay.
Looked like I trained that.
Yes, it's almost like you did. Okay, so but we have another answer. So please, Sven, go ahead.
Yeah, so while Big Crunch might be more like nice to think of, the reality is probably more depressing. Our universe is expanding and the dark energy is leading to an accelerated expansion. So this expansion will get more and faster and faster. It will lead to the fact that at some point we can't even see other galaxies than our own anymore. And then at some point we will not have enough material to form stars anymore. So the last stars will die out much, 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 much later. The last black holes will evaporate due to Hawking radiation. The universe will get colder and colder and colder. At some point, probably even protons are going to decay. So even the matter itself is going to decay, and the universe will just be basically a big pile of nothing with some lonely photons traveling through it, which is a bit depressing. But this is unfortunately what all the data that we have suggest.
All right. I'm actually not sure what is more depressing, but there's
I mean, the big crunch would then allow for like, I mean, some kind of cyclicity, right? Big crunch and a new Big Bang, and it doesn't end forever or something. I would prefer that.
Okay, and it's whatever you prefer. There's only one correct answer, so you get to tell us in the chat what you think, who is correct. And yeah, I think they both think that they're correct. But one is lying. One is telling you a blatant lie. So who is it that told you a lie just now? You can raise your signs. Now it's the false crown.
It's a dual crown.
Okay. It serves a dual purpose. That's really smart.
So truth and lie are two sides of the same crown. Something.
I always wanted to wear a crown.
Good point. Yeah.
Okay, so the big crunch is incorrect.
Yes.
So why is that?
Yeah, as Sven said, as Eleni said before, so like Sven did before, I technically did not lie, and there was a large amount of time in the history of doing actually astrophysics that we believe that there's only one way that the expansion has to slow down, and it only changed, marked by the Nobel Prize in 2011, that we changed our view, and that we actually acknowledged the existence of a substance which we just call dark energy in the lack of knowing matter, and that has some repulsive force that we cannot really pinpoint at this time.
Yes, I mean, I think it's still for a long time it depended like really on the ratio of the different energies in the universe, what will happen, right? So, but right now we are pretty sure that the big freeze is correct. Sort of depressing, but I think we still have some time left.
It's still better than Big Rip.
Yeah, I think the proton decay is like 10 to the 1,000 years or something like that. So there's a bit of time. Yeah.
So so that you know your protons are still safe for some time.
Yeah, it's like the typical time span you need to finish a PhD.
Yes. It would have also been a good analogy for the age of the universe, right?
None of us will live to see it, so.
Well, I mean, some people manage to finish their PhD, so I guess it can be done. Okay, let's move on with the next questions, which is like pretty fundamental. The question is, can we prove scientific theories right or wrong? So one answer is the verificationism, and one is the falsificationism. And what that means, and which answer they will give you, we will start with Sven presenting his answer to that question.
Okay, so I'm not sure if I will talk one entire minute to this because, I mean, you know the term scientifically proven, right? I mean, the entire goal of science is to prove theories correct. So, for example, we have the theory of gravity, the theory of evolution, that are scientifically proven. The opposite is impossible. For example, I cannot prove that pink unicorns do not exist. Just because I haven't seen them and no one else has seen them doesn't mean that they don't exist. However, if I ever saw one, I would have proven that they exist. So yeah, in science, we can only prove theories true. And yeah, you cannot prove a negative.
Okay, that was short enough and concise. But we have a different answer that Maud will present to you now.
Yeah, falsificationism is the answer I'm going to defend here. So in science, we have theories that try to match real life. And we can never prove that a theory is right, because for that we would need all the parameters, all the details. We would need to be God, basically. So that's not what we do. What we do is that we do a lot of tests and we say, okay, this theory that we have, it works for all the tests we did. So we see that so far it's working. And where am I going with that? I lost myself.
The time is.
It's pretty hard to lie convincingly, right?
I'm not lying. But yeah, you get my points. Yeah, okay, I got my example back. If I still have time.
But that is, we don't have time for that now. So
okay. I'm done then.
That's it. Okay, I think you did make your point. So again, you decide in the chat who you think is right, Sven or Maud. Yeah, there's only one correct answer, as always, to this question. This would be a good time to do like the this Jeopardy thinking music. I don't think we have that right now.
Felix.
Yes.
Felix, can you prove that there's only one right answer?
This is what we will find out now, because the correct answer is Maud's answer. It's falsificationism. So Sven, please tell us why you why did you tell us such a convincing lie? Why was it a lie?
So yeah, the thing is that this scientifically proven is something that we usually say yeah, this is true to a reasonable amount of doubt. So for example, when I let go my pen, it will drop. You will probably believe me, but there's no way to be 100% certain. And one example that I gave actually contradicted myself a little bit, namely the theory of gravity. The theory of gravity of Newton is not the correct one. It's not the final one. It has been extended by general relativity, and it will probably be extended more and more and more. All these theories that we make are just models that we use to describe reality, and no model can be perfect. So
that was my example. I lost it because of you, because I was like, oh, he's using the same example as me. You got me all confused.
I'm sorry.
No, that's fine. That's life. At least it was funny because I was telling the truth and I got confused. So.
And it was very
I had to use that.
Well,
you see, we didn't rehearse that. We just thought about it on our own, and this is what happens.
Yeah, it's like a real duel, a battle of science. So
and right, I'm sorry. the existence of pink unicorns is not a scientific theory. So my counter example was like the scientific theory is something that describes a large amount of independent observations with some model, has nothing to do with pink unicorns or anything. Okay. Sorry for interrupting. I just
So I invite the audience to scientifically disprove the existence of pink unicorns. So, all right, let's do the next question. Also, might have gotten a hint. We have like, it's sort of fits perfectly with what we already talked about today. So if you paid attention. The question is, what was before the Big Bang? Either nothing, a total and absolute vacuum, or there was no before. And first, Maud will present her point.
Yeah, so before the Big Bang, it was vacuum. You might think, okay, but that's weird because how could something, come out of vacuum? But maybe you've heard before of quantum fluctuation. It's very well known in quantum mechanics that from vacuum, thanks to the fluctuation, particles are being created. So that's basically what we think happened. They were vacuum and the universe emerged from this vacuum, from the quantum fluctuation.
Okay, that was just short enough. Didn't have to mute you or something. Okay, and we have a different point of view, which comes from Sandra. So please go ahead.
What was before the Big Bang? This is like number 1 or 2 party questions I get whenever I reveal I do astronomy. Yeah, there is no before. Before indicates a time, but in our understanding, time started at or maybe after the Big Bang. So it's like asking what is darker than black? It's like there is no such thing. So there may have been a something, and it may had lots and lots of dimensions of all kind, but in the event of the Big Bang, we had like a split of 4 nice dimensions, 3 in space, 1 in time, actually good thing, only 1 time direction, by the way. And you cannot contact even other dimensions. So this whole question doesn't make sense. And there is no before. It's not a question of science, it's a question of philosophy, if you really want to talk about what was before.
Again, just in time. Yeah. So you said the question does not make sense. So okay, you the audience get to decide who is right here. Yeah, just give you a few seconds to think about it while you're listening to my voice. Two opinions. And one answer is correct. Okay, let us reveal who is correct. The true crown is on Sandra's head, so yeah, she is correct. It's the question. It's kind of interesting that the question doesn't make sense, but it's true. So Maud, can you tell us why you were wrong here?
Yeah, well, Sandra explained it really well already. It's more a philosophical question because if you take it really as a physicist, you speak when you talk about what was before the Big Bang, you already speak in terms of times, but we think currently that time started at this very moment. So how could you even speak about time at a point where time wasn't even here? It's just a very philosophical question, and the question in a physical sense is not to be answered. It's just nothing yet.
So we sort of reached the limits of our language and our minds, right? So
yeah,
it's really amazing.
Yeah, exactly. It's like physics is your language, and there is no word to describe something before time even existed.
Yes. Okay, we have one more question for you that is maybe not as philosophical as the one that we asked you just now. And the question is, which object is better, in quotes, at producing energy? And we have either black holes or stars as candidates. So our first response comes from Sven. Please go ahead.
Yeah, so black holes are much better at producing energy than stars. Black holes produce energy when matter falls inward towards the black holes. It accretes in a disk around it, rotates, and there's a lot of friction, and that gets heated up a lot. Now, black holes are by far the densest objects in our universe, and the gravitational forces close to a black hole are so strong that not even light can escape. So these forces, and thus also the temperatures that are involved there, are just beyond anything else in the universe that we know of. So yeah, in part, so this leads also to a much more efficient energy creation. Another argument is that active galactic nuclei, or quasars, they are sometimes brighter than the entire galaxy that they're in by a factor of 1,000, whereas they're only as big as our solar system, more or less. And to produce this much energy on such a small space, this just wouldn't be possible if they were only as efficient as stars.
Okay, again, just in time. Okay, we have a different point of view on that. So, Sandra, what is your answer for this question?
Yeah, so this is an easy one. Think about an atom. It must be stars, by the way. Think about an atom. It has electrons orbiting the protons and neutrons. And everyone at home can light a candle, right? This is like a redistribution of all these electrons around that. But if you want to exist the core, if you want to have a distribution of these nucleons, if you want to destroy them, you have to go to a facility like the CERN. And then you need a lot of energy to break an atom apart, right? Now, inversely, if you need a lot of energy to break them apart, imagine how much energy you gain by actually fusing them. So we are currently trying to do that to solve the energy crisis. And it's an ongoing project. And nuclear fusion is the only thing in the universe. One supernova explosion outshines the whole galaxy. And this is an explosion.
Okay, I had to mute Sandra there because the minute was over. Okay, we have two answers for you. And you decide, again, this is your last chance to decide today for our last question, who is correct? Is it either Sven or Sandra? They both want you to vote for them.
I'm right. Obvious.
Okay. So let us reveal now, like, who is false and who is right. It is actually black holes. So why is it not stars, Sandra?
Yeah, so in this explanation, if you have listened to Sven, I omitted, so everything that Sven says is true. And I omitted the tiny detail that the energy you gain from nuclear fusion, which, you know, if you just look at the energy that is involved, it's much more than the black hole does produce in the end. But the other thing you release, the thing you're interested in, the thing that travels outward, is only the energy difference that you get from fusing a couple of things to a new thing. And the energy difference is actually not that high. So for example, for fusing 4 hydrogen into 1 helium, you only get a 1% energy efficiency. And this is not a lot. A light bulb can do more efficiency-wise, not energy release-wise.
So if we want to solve the energy crisis, it's best to get us a black hole, have it accreting matter, and then, yeah, extract the energy from that.
And my example with the supernova explosion was totally off because my answer was stars and not, you know, the violent death at the end of the life of a star.
Well, like, one could argue that that's still coming from stars, right?
Actually, yeah, now that you say it.
AGNs are still brighter than supernovae.
It's true. They are still brighter.
Depends on how close they are.
Since I'm studying the outflows from black holes for my research, of course, I had to stay silent in this one until the end. But of course, it is black holes. Okay, so thank you everyone for presenting your answers. I think this was very exciting, and
Yeah,
I hope
it
you
was
had.
fun.
I hope you
It was
had
a lot of fun.
for me as well. So I hope you had a good time in the chat, and you're now a bit smarter than before, or maybe you were smart from the very beginning and had every answer correct. Then also congratulations to you. Okay, and with that, I will give it back to Laila for some closing thoughts.
Yeah, thank you very much. Thank you very much, Felix. And thank you very much for this really nice game. I think I was almost fooled a couple of times. And I also want to announce the winner, who was randomly picked from the people who participated. And the winner will be Markus Schneider. And you can either leave your contact email in the chat, or you can write an email to our aotbonn@gmail.com address, and then we can contact you about how to send you your prize. Let me just thank everyone again for playing with us. Thank you, Eleni, for your really, really awesome talk. Thank you, everyone, for watching. And lastly, I just want to close this event for today. I had a lot of fun, and I hope to see you again next time in a month's time on the 23rd of February, where we will be again virtual. But that doesn't mean that we cannot have a lot of fun with 2 awesome talks. And yeah, looking forward to it. So thank you very much. Have a good night, everyone, and see you in February. Okay, the stream is